Hello everyone, this is Professor He. Nice to see you again. The topic of this subtask is about the forms of energy. Energy can exist in numerous forms such as thermal, mechanical, kinetic, potential, electric, magnetic, chemical, and numerical, and their sum constitutes the total energy E of a system. Thermodynamics provides no information about the absolute value of the total energy. It deals only with the change of the total energy, which is what matters in engineering problems. Thus, the total energy of a system can be assigned a value of 0 at some convenient reference point. The change in total energy of a system is independent of the reference point selected. The decrease in the potential energy of a falling rock, for example, depends only on the elevation difference and not the reference level selected. In thermodynamic analysis, it's often helpful to consider the various forms of energy that make up the total energy of a system in two groups, macroscopic and microscopic. The macroscopic forms of energy are those a system possesses as a whole with respect to some outside reference frame, such as kinetic and potential energies. The microscopic forms of energy are those related to the molecular structure of a system and the degree of the molecular activity, and they are independent of outside reference frames. The sum of all the microscopic forms of energy is called the internal energy of a system and is denoted by U. The macroscopic energy of a system is related to motion and the influence of some external effects such as gravity, magnetism, electricity, and surface tension. The energy that a system possesses as a result of its motion relative to some reference frame is called kinetic energy. The energy that a system possesses as a result of its elevation in a gravitational field is called potential energy. Now we talk about the terms and units used for expressions of energy. Kinetic energy, EK. Kinetic energy per unit mass, EK. Potential energy, EP. Potential energy per unit mass, EP. Total energy of a system, E. Total energy of a system per unit mass, E. Mass flow rate. Energy flow rate. The topic of this subtask is about some physical insight to internal energy. Internal energy was defined earlier as the sum of all the microscopic forms of energy of a system. It is related to the molecular structure and the degree of molecular activity and can be viewed as the sum of the kinetic and potential energies of the molecules. The portion of the internal energy of a system associated with the kinetic energies of the molecules is called the sensible energy. The internal energy associated with the phase of a system is called the latent energy. The phase change process can occur without a change in the chemical composition of a system. Most practical problems fall into this category, and one does not need to pay any attention to the forces binding the atoms in a molecule to each other. An atom consists of neutrons and positively charged protons bonded together by very strong nuclear forces in the nucleus, and negatively charged electrons orbiting around it. The internal energy associated with the atomic bonds in a nucleus is called chemical energy. During a chemical reaction, such as a combustion process, some chemical bonds are destroyed while others are formed. As a result, the internal energy changes. The nuclear forces are much larger than the forces that bind the electrons to the nucleus. The tremendous amount of energy associated with the strong bonds within the nucleus of the atom itself is called nuclear energy. Obviously, we need not be concerned with nuclear energy in thermodynamics unless, of course, we deal with fusion or fission reactions. A chemical reaction involves changes in the structure of the electrons of the atoms, but a nuclear reaction involves changes in the core or nucleus. Therefore, no atom preserves its identity during a chemical reaction, but loses it during a nuclear reaction. The thermal energy includes sensible and latent energies. The internal energy includes sensible, latent, chemical, and nuclear energies. The total energy of a system can be contained or stored in a system, and thus can be viewed as the static forms of energy. The forms of energy not stored in a system can be viewed as the dynamic forms of energy or as energy interactions. The dynamic forms of energy are recognized at the system boundary as they cross it, and they represent the energy gained or lost by a system during a process. The only two forms of energy interactions associated with a closed system are heat transfer and work. An energy interaction is heat transfer if its driving force is a temperature difference, otherwise it is work. In daily life, we often refer to the sensible and latent forms of internal energy as heat, and we talk about heat content of bodies. In thermodynamics, however, we usually refer to these forms of energy as thermal energy to prevent any confusion with heat transfer. A distinction should be made between the macroscopic kinetic energy of an object and the whole and the microscopic kinetic energies of its molecules that constitute the sensible internal energy of the object. The kinetic energy of an object is an organized form of energy associated with the orderly motion of all molecules in one direction in a straight path or around an axis. In contrast, the kinetic energies of the molecules are completely random and highly disorganized. Okay, that's all for this task. Thank you very much, and see you next time.